Okay, so here we are. We learned about three different color scales: the diverging color scales, the sequential color scales, and the qualitative color scales. And it turns out applying these color scales really just depends on the data you have. If your data is ordered, if there are numbers or if there are grades or anything that implies an order, use a sequential color scale. If there's anything in your data that has a diverging character, such as low values and high values and the thresholds and such things, use a diverging color scale. If your data does not imply any order, then use a qualitative color scale where all the colors are perceptually equidistant. Now, what happens if you violate these rules is something that we're going to see in the following example. In this country, we have a value per region, and we can see from our scale that these values range from -10 on one side to 10 on the other side. If we use a sequential scale, in this case not really color but luminance, we're going to see a gradual change in patterns, and we see that the northern parts and parts of the south and parts of the west of these countries are dark values, and there's a gradual flow because the rest of the country has really low values. We use a diverging scale, which actually could be an option in this case because we have negative values and positive values. And we use this, such as this color scale on the bottom left, then we end up with a very different picture. So suddenly we don't have this center, south, east patterns, but now we see a north-south divide in a sense. Now this is not due to the values in the south are below 0 and the ones up and the ones in the north are above the 0. No, it just depends on how we perceive these colors. Because what you're realizing is that the blue on the lower end of the scale, -10, and the purple on the upper end of the scales, magenta, purple, are perceptually pretty close. So that's how these color scales cruise our perception of these values. And if we were to use a categorical color scale, where there's no implied order between colors, our map would look like this. Now what we see here is no overall pattern anymore. We can't see that there's a gradual change from this part of the country to another part of the country. Yes, we can see that there are so and so many green counties, and we can probably compare these values, but we can't say, looking at the green country, is the surrounding gray country higher in value or lower in value, and what is the orange and what are the other colors. There's no intrinsic mapping, and we don't see the overall pattern in this map. Now this leads us to a specific problem which is often encountered in scientific representations. Because you can argue, well, there is an intrinsic ordering in color. Why can't we use color for ordering? Because you can have as many values as you want, and you can order them according to how they're appearing on the spectrum and the natural color spectrum, which then gives you rainbow color map. But let's look what happens if you apply this famous rainbow color map to actual visualizations. Here's a common example from science where we have flow visualizations, and the color in this case represents probably the density of this fluid. This goes from 0.4 to 2.4 on the other side. If I show you the same picture in a diverging color scale, we see suddenly something like this. So suddenly we start perceiving shapes and overall patterns. And even more than that, we also see really low-level patterns, small changes which are completely lost in this part due to all being cyan. So this is an interesting case where the color map is not showing all the examples, and there are many, many, many more examples that you can find where the rainbow color map is not used well. Here's an example from geography, which maps the height on this map. What is good about this map is we can see which areas have the same height. So we can see that these areas over here, the green areas, are somewhere similar to the areas on this side. We also can see that these are the red areas that are sticking out. However, what this map introduces are sort of artifacts, because if you look at these borders, those of you who know this map know that these borders do not exist in reality as strong as they are. So the rainbow color map introduces artifacts, it introduces steps which are due to the way that we perceive color. So whenever our brain switches from one color, magenta, to another color, dark blue, cyan, green, yellow, it introduces these steps, and these steps become visible and it can occlude actually information. Here's another example where we're using a divergent color scale or a sequential color scale. It's not specifically clear in this case. And you can see that these steps are way less prominent, and you can better perceive the overall shape of the profile of this map. And of course, this is true for other visualizations as well. Here we have the table. If you look on the table of the right, the number 4 here sticks out way better than in these examples, for example. And why is this the problem? So the rainbow color map has many different problems. Among one of these is the lightness, the usage of lightness, the perceived lightness of different colors. So here's our famous rainbow color map, and we can see on the right side the lightness distribution of these colors. So it goes from very light to some gray to then some dark, but there are these kind of steps in between. And this is what introduces eventually the steps in this map and in all the other visualizations we have seen so far. And if you look at other rainbow color maps, there might be even worse in terms of light. So this one has a dark area here, has a dark area here, and a bright area in between. It has a light area here, a light area here, and another light area on this side of the scale. There are some rainbow color maps, such as this one, that has a gradual change in darkness. So all the dark colors on the right side and the bright ones are here. So this is what we kind of start perceiving here, though this blue is a very clean, and this purple is also really green, as well as this purple is also very light, as well as this yellow. So it's not said that this color map does not introduce steps. In fact, all of these color maps, most of them that you can see here, will introduce these steps. And the more you look at them, especially this one, you're going to see these discrete bands in the color map, which of course then will guide your perception of a real color map. So let's wrap up briefly, because color maps are a complicated issue, and you're going to read you're going to find lots of literature on how to not use color maps in a sense. On the positive side, if we have many different values, the color map can show us these many different values better than a gradual color map, a gradual sequential color scale. We can also compare many similar values, as we have seen in the example with the map. We can see which areas of the map have the same height. On the other side, colors are hardly orderable. We cannot say if green is higher than purple by perception. We have to do cognitive load, we have to decode and think about where these colors lie, and this is not the point of perception. This is cognition. Visualization, most of the time, is about perception. The rainbow color map also introduces sharp jumps in values when our brain switches from one color to the other. It can hide overall pattern, as an example with the flow, the fluid visualization. It overemphasizes certain values, so some blues or some yellows can really stick out. And it is not black and white safe, as we've seen in the previous slide, as well as it's not colorblind safe. We talk about colorblindness in another lecture. However, if you want to use a color map, there's only one rule: use a linear color map. Use a linear rainbow map as an example B here, because this one avoids changes in lightness as we see in the example A. So A is really the example that you would get from the HSB color model as the U, but in the center one we have a nice transition between all these colors. However, there are counterexamples, as always. This is a nice example where the color map is used to show ordered and actually quantitative data. If you see on the bottom on the legend, each of these bar charts shows the distribution of deprived areas in this specific region. So we have blue are the most deprived, and then it goes through some green and yellow up to some purple for the most affluent. Yes, for the most affluent. However, the color in this example is a really nice example of how you can use color to make lookup and comparison between these small multiples easier. Because now it is very easy to compare this beige value to all the other beige values, and you're going to see which one is the highest in this category, for example. The same holds for the dark blue. You see the dark blue sticking out here, these two counties, as well as the purple ones on the other side. So this is a good example of where color helps you making relations from one part of the visualization to another one. And since we haven't coded the height, the percentage here actually, we don't necessarily, and as individual bars next to each other, we don't need so much the legend to figure out which bar this is. We just see this bar is to the right of this bar, which is to the right of this bar, and so on and so on. So we can see, yes, the bars on the right side, more affluent, the bars on the left, less affluent. The color is an additional, we call this redundant encoding to show, to make lookup and comparison across these small multiples easier.